All right, so this is lecture 17, and today is interesting. Is lecture 17, how that happened? The 17th of February, okay? Okay, so what did we um, discuss last time? We said that we are now covering or continuing rigid body equilibrium, but we are extending that to the analysis of a structure. So, in a way, we are introducing structural analysis, a very basic, fundamental structural analysis, which is um, finding the internal forces in structures, and we started with frame structures, okay? Let me bring it down because otherwise it's not going to be as uh, clear. It's going to be a little bit fuzzy from a distance. Do you clearly see the page? All right. So we started with frames, and let me just simply summarize the steps that I strongly recommend you follow. And please make sure you know, do your best not to just when you're given a frame problem, just to start jumping here and there and trying to just find the answers. Follow the problem methodically, and this is the methodical approach that I'm suggesting. First step, draw an X or Y coordinate. Second step, draw free body diagram of the structure as a whole without cutting it, of the structure as a whole, okay? I put um, a also a note here that as a next step, and I put an asterisk here, watch out for two force members, okay? You may not have this step if you don't have a two force member, but it is something that I always warn you, watch out for it, okay? So step number 4, you draw the free body diagram of all members by taking all members apart. And then step number 5, which is the heart of the problem, okay? Start with a free body diagram that has the least number of unknowns, okay? Try to solve for as many unknowns as you can, and then move to the next free body diagram. So these are the 5 simple steps that I strongly recommend that you follow. So let's start with, see how we can apply these and demonstrate that through an example problem, okay? So this is the problem I want to do here, okay? Let's say you have a frame that has these uh, number of members, okay? You have a frame, okay, this is one member, okay? I should not have done it so long because I want to make sure that I do the scaling right, okay? All right. So this is the frame, the member, okay? Another member connected to that comes down, okay? And then, sorry, this is a solid member connected to another member. This is 0.2 meters. This is 0.4 meters, 0.4 meters here is pinned here, point A, you have a pin connection. You have another member connected to this, okay, like this, okay, and this comes down 0.3, turns around. All right, so drawing it took longer than solving. So let me label these A, B, C, D, E. You have a load here, and you have a load here, right in the middle here, 0.2 meters. So you have 2 kilonewton force here, 5 kilonewton force here, and this is F. So you have a frame that consists of 3 members connected to one another, and these 2 loads that are applied externally. Okay, so first step number 1, draw an X, Y coordinate, right? Step number 2, draw the free body diagram of this structure as a whole. I'm not going to do a separate free body diagram. I'm just going to get rid of these supports here and put back the effect of the forces that they represent. Okay, so set up the free body diagram that way. So this is the free body diagram of the structure. So this is step 2. Any questions? All right. So now let's take all these members apart. I have, let's start with this member. I would draw that one. Okay. Okay. So let me label also these free body diagrams. What I will do, I would label them. Let's call the free body diagram of this whole structure as number 1. Draw this one, and I call that free body diagram number 2. So at this end, you have these forces, AX, AY. In the middle, at point B, you have a pin connection between these 2 members. That represents 2 unknowns, BX, BY. I always assume these unknowns in the positive direction of the coordinate system. If it happens that after solving the problem, the assumed directions are wrong, you change them, right? So that's the same thing at point D, dx, dy. So this is the next free body diagram. Let me call this free body diagram number 2. Okay. How about this guy? Let's draw that one. Okay. This is that free body diagram. So this is point E. You have an applied load 2 kilonewton. At point D, you look at point D. This is point D.
Can you scoot your paper up a little bit?
Sorry.
Thank you.
This is point D. So point D is the point of connection of these 2. I assume the unknowns here on this member acting that way, and it is critically important that make sure do not make this mistake. You have the arbitrary choice of assuming these unknowns in any directions you want the first time they appear. But when you go to the next member and you're drawing the free body diagram of the next member, you need to follow the 3rd law of mechanics. That is, if these are the unknowns acting on this member at that point, at that same point, that is a point of connection of these 2, you need to consider forces in the opposite direction. You cannot, on this member, also assume same directions. If you do that, I can guarantee you that your results will be wrong. okay? Then you have this applied load, 5 kilonewton, and at point C, you also have these two unknowns. The first time they disappear, so I'm assuming them to be in this direction. And this is free body diagram number 3. One more free body diagram of the last member here, okay? And that is this member. Member B, C, F. On this end, we already know this is the assumed direction. At C again, it is a point of connection of these two, right? You assume that CX and CY are in this direction on this member, so you need to put them in the opposite direction here, CX, CY. Same thing at B. You assume this is the point of connection of these two members. If you make those at that assumption that they're acting in that direction on that member, here they should be the opposite, BX and BY. Okay? So this is free body diagram number 4. And you're done with step number 3 and 4. There was no two force member. You drew for all the free body diagrams, right? And as you can see, how many free body diagrams you have? 1, 2, 3, 4. So the next step is you start with the free body diagram with a minimum number of unknowns. Remember, minimum number of unknowns. You start with that, try to solve for as many unknowns as you can, then move on. So I have 1, 2, 3, 4, 5 here. 1, 2, 3, 4 here. 1, 2, 3, 4, 5, 6 here. 1, 2, 3 here. So obviously, which one is the best to start with? Free body diagram of the structure as a whole. Doesn't mean necessarily that is always the case. It happens that in this situation, free body diagram of the structure had the least number of unknowns. So I will start with that. To start with that, you've seen this, you've had this problem before, right? You're looking for to find the external unknown forces. You have 3 unknowns. I write down here, this is free body diagram number, and I want to solve this. 3 unknowns, take the summation of moments about point A to get rid of those 2 unknowns and find this one RF. So I get RF counterclockwise. This distance is given. I forgot to give you, this is 0.2. This is 0.3. So RF times 0.5. Okay. What if other forces you have? 5 times this distance, which is 0.2 and 4.6, negative. So 5 times 0.6, 2 times 0.2, this is 0.2, 4.8 to 1, so 2 times 1 equal to 0. That will give me RF. That comes out to be 10 kilonewton. Came out to be positive. That means the assumed direction is right. As soon as you've done that, put a check mark on those unknowns wherever they appear. We have it here, you have it here, because that helps you to see immediately how many unknowns are left on each free body diagram. So let's finish what we started here in this free body diagram. Right, summation of forces along x is equal to 0. So you have just RF, which is 10 kilonewton, plus AX is equal to 0. So AX comes out to be negative 10 kilonewton. What does that mean? The assumed direction for AX was wrong. So I would immediately correct that here and correct it wherever else it appears. Here. All right. Now, so this is 10 kilonewton. Summation of forces along y is equal to 0. I have AY minus 2 minus 5 is equal to 0. I get AY. That comes out to be 7 kilonewton, positive. So the assumed direction was right. Get rid of this. And here. Also, it is a good habit if you have completely used everything or exhausted all options on a free body diagram, put a check mark, put a cross on it, so you know that you're done with that free body diagram. It's useless from that point on, okay? So now you have what, 1, 2, 3 more free body diagrams to solve for all the remaining unknowns. So look again. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4 unknowns. So you can choose any of these free body diagrams you want. However, I make an observation here. If I choose this one, and of course, the best option to use when you start using equations of equilibrium are starting with summation of moments about a point. If I take summation of moment about either this point or this point, which is a point of intersection of two unknowns, I still end up with two unknowns in the moment equation. However, if I choose this one or this one, and I start, let's say, with this one, take summation of moments about point C, I end up with only one unknown, which is dy, because dx also goes to that point. Same thing here. So instead of starting with, although all of them have the same four unknowns, I will start with this one or this one. So let's start with number 3. Start with number 3. If I take summation of moments at C is equal to 0, I have only one unknown, and that is dy would be clockwise, of course, negative dy times this distance, which is 0.8, okay? So I have dy times, I'm sorry, dy is 0.4, okay? That's this distance. Then you have this one would be positive, so you have 5 times this distance is 0.2, and you have plus also 2, which is also clockwise, counterclockwise. I'm sorry, that would be, they're all clockwise, so that would be negative, and this would be negative. 2 times this distance, which is 0.6, is equal to 0, okay? So once I solve for this, I see that I end up with dy that comes out to be negative 5.5. That means the assumed direction for dy is wrong. So I have to change it here, okay? And put a check mark because I found it. Where else does it appear? Here, right? So I change that here and put a check mark on it, okay? Now, let's go to summation of forces along y is equal to 0. I have cy minus 5 minus 2 plus 5.5, okay, equal to 0. And that will give me Cy comes out to be 1.5 kilonewton and comes out to be positive. So I found this one, okay? I have one more equation to use, and that is summation of forces along x is equal to 0. So summation of forces along x is equal to 0. That gives me Cx minus dx is equal to 0. And that's it. I have exhausted all my equations of equilibrium on this free body diagram, but I could not solve for dx and cx. So what do? I move to the next free body diagram with least number of unknowns. Here I had found Cy. So if I move and to the next free body diagram, again, look at the two that I have remaining. 1, 2, 3 unknowns, 1, 2, 3 unknowns, right? So I can choose either one, but I would go with this one. Why? Because I can see again, if I take summation of moments about point B, I can quickly find one of the unknowns. So I'm going to move to free body diagram number 4. And I take summation of moments about B is equal to 0. If I do that, I have negative Cx times this distance, which is 0.2, okay? And then, so I get summation of moments about this point, right? So the only other force I have is this one, which is counterclockwise, and that's 10 times this distance, 0.5, is equal to 0. And Cx comes out to be 25 kilonewton, positive. So found Cx, put a check mark here where it appears, and that's also appears here, right? But before I go any step further, I say, wait a minute, I had one equation here that I couldn't solve. Now I have found Cx, so I can solve that. And I can see that dx, which is going to be equal to Cx, would also be 25 kilonewton. So apparently I have now this one. So this free body diagram is also out of picture, right? Let me go back here, which I had left unfinished now. So in that free body diagram still, I can use summation of forces along x is equal to 0. I have negative bx, negative 25 plus 10 equal to 0, and bx comes out to be negative 15 kilonewton. What does that mean? That means the assumed direction for bx is wrong. So I have to change it here, put a check mark here, and I have to change it here. Put a check. Okay? All right. So, and then correct that one. So now summation of forces along y is equal to 0. Okay? I have cy, which is 1.5 minus by is equal to 0. That means by comes out to be negative 1.5 kilonewton. Again, negative sign means the assumed direction here is wrong. So I have to correct that. Done. I have to correct it here. This is downward. Done. Okay? So bx is 1.5. And what happened now? I have solved for all unknowns. And as I promised, I ended up with one free body diagram that I did not use. And that is this one. Remember, I told you in frame problems, if you do the problem methodically the way I am strongly recommending you to do that with these 5 steps, you always end up with one unused free body diagram, which is great. If you do haphazardly, not follow this methodical approach, you have a mess and you don't end up with a free body diagram that you haven't used. So I'm going to use this to check my answers, verify those answers. Let's do that. You should have, so I go to free body diagram number 2 and use that for the verification. That means summation of forces along X have to come out to be 0. Summation of forces along Y have to come out to be 0. And summation of moments about any point has to be 0. So let's start with this one. Let's add up summation of all the forces. We have all of them, right? AX, -10, BX, which is now in this direction, -1.5, DX, I'm sorry, -1.5, or what was 15, no, I'm sorry, -15, okay? DX, 25. See, that goes to 0. So those answers are verified. How about summation of forces along Y? I have AY, 7, right? Minus BY, which is -1.5. And negative DY, which is 5.5. See, this goes to 0. So this free body diagram verified the answers that I have found by using all the other free body diagrams are correct. So that makes this a habit of using the unused free body diagram that you always end up with to verify your answers. Any questions before I move to the next problem? No questions? All right, so let's do another problem, okay? This is a good problem. This was, in fact, a problem we had given in the final exam last term, okay? So this is a problem. And this is a problem, as I told you earlier, that one of my colleagues made a mistake in drawing the free body diagram, okay? So this is a frame that consists of a few members, okay? Let me draw this whole frame first, then we'll talk about that. So you have a structure that is pinned here at this support A, and there's a roller support at point F. Let me label everything: A, B, C, this point D, this point E, and F. Okay, I have already labeled that. So this frame is designed to carry a 300-pound load through this pulley that is attached to the tip of this member. And let me also give you all the dimensions that you need. 4 feet, 4 feet. This is 6 feet. This distance is 3 feet. And the radius of this pulley is 1 foot. So this distance obviously is going to be 1 foot. So you're asked again to find all the unknowns in all the unknown internal forces in this problem. Step number 1, this is my x, y coordinate. Step number 2, draw the free body diagram of the structure as a whole. Here you have a pin, so you have these two unknowns. Here you have a roller, so you have one unknown. So this is free body diagram number 1. Okay, so free body diagram of the structure of the whole structure. Okay, number 3, watch out if you have any two force members. Any two force member? I don't see it here. I don't see any member that is only connected at the two ends. Two ends are pin, no load acts along that member. So there is no two force member here. Therefore, draw the free body diagrams of all other members by taking everything apart. So let's take apart the pulley. The pulley is carrying a load of 300 pounds here. From physics, you remember if this is a frictionless pulley, you have to have a 300-pound force there. So this is D. I assume unknowns in this direction. Okay. This is a mistake that my colleague had made. And many people do that. And that is when you have a pulley. Do not cut the pulley from the structure when you're drawing the free body diagram of the structure as a whole. The free body diagram of the structure means you do not touch anything internal. Okay? This is your structure. Don't look inside. Keep it intact. Only cut the structure from its supports. Okay? Because otherwise you end up with these two forces, a mess. Anyway, this is the free body diagram number 2. What is the next one? Let me draw this free body diagram of this member. This is member B, E, D. So at E, D, you had assumed forces acting from this member to the pulley to be in these directions. So obviously, at this end, you have dx and dy have to be in the opposite direction. At point E, I don't know what direction they are, so I assume this direction. Same thing at point B, px and by. So this is free body diagram number 3. How about this member? Let's draw that free body diagram now. Okay, that's this free body diagram. You have point E here, which is connected to that member. So unknown forces should be in the opposite direction of what you had assumed here. At point C, I don't know, I'll just put them Cx and Cy. That's the first time they appear. And then at point F, I have this force, but you also have, at this point, this cable is connected to this member, so you also have an applied load. Okay, so that, let me erase this so you can see the whole page and all the free body diagram all in one place. Okay, all right. As long as it is not fuzzy. Okay, so these are, okay, so this is your free body diagram number 4. One more, this member. So point C, which is connected to that member, you had assumed on this member, Cx and Cy are in that direction. So on this one, have to be the opposite. And at point B, okay, you had connection with that member. So the forces of Bx and By on this member should be in the opposite direction. Then you have an A, AX, and AY. And this is free body diagram number 5. So you have 5 free body diagrams. Okay.
When it's the forces that were like external, do you keep the same direction?
Oh, am I glad you asked that question, because that question actually came up in the other section as well. Let me elaborate on that, because the question you asked is extremely, extremely important. And thank you for asking that. What she's asking is a great question. See, you have this structure here. This is that. So I said that when you draw the free body diagram of this structure, what do? You're removing this. So the action of this pin on this structure is assumed to be in this direction. So what she's saying is, how about if it comes to this member? Should I keep it, the unknown forces acting at A at the same direction or not? Yes. Why? Because of this. When you're separating this, right, from this structure at this point, you have this pin connected to this structure, right? So what is the action of this pin support at that point is exerting these two unknowns, right? So this pin is the same pin here, right? So external, if you have a member, that one end of it used to be an external support, the directions you have assumed for the external support for the free body diagram of the whole structure would be the same for on this free body diagram of the member. There's another reason we are doing it. Look at this member. It was connected to this mechanism, which we call that a pin, right? So when I say separate this structure from its environment, you would say that, what I'm doing is actually I'm separating it here. So the unknown forces that I'm assuming for the structure as a whole are actually here, right? You can think of it that way too. But then you need to look at it that this is a device then. So if these are the forces externally, you're separating it from that member, you have these forces at this end of this device. And this is what is connected to here. So you end up with forces in this direction, that same member, which happen to be the same. So this is a little bit confusing, this approach. Just remember, when you have external forces at the support, those external supports on the member that you're drawing its free body diagram will stay in the same direction. But thank you for asking that important and very good question. Does that clarify it?
Yeah,
Did
that
I
helps.
answer?
Thank you.
Perfect. So just remember, would be the same. So how many unknowns you have on each free body diagram? 1, 2, 3. Here you have 1, 2, 1, 2, 3. I'm sorry, 1, 2, 3, 4, 5. 1,
Professor,
2,
may I
3,
ask a
4.
question?
Yes.
How come D, like the pulley at D, is allowed to be its own free body diagram that we can like sum everything to 0 at? Like, is it because the pulley isn't moving?
Oh, good question. See, pulley is a piece of a structure, isn't it? This is a pulley that is connected to D to the rest of the structure. So this is a piece that you're taking it apart. In other words, there's a pin that connects this pulley to, in other words, this is a component of a structure. So when you're taking it apart from this pin, the action of the pin here would be these two reaction forces, which on this member act in the opposite direction. Did I answer it right? Your question?
Oh, okay. Yeah, that makes sense. Okay, thank you.
So the pulley is always a good one because you pulleys, if you draw all the free body diagram correctly, you see that that's the free body diagram with the least number of unknowns. And that's where you start in this problem and not necessarily with the free body diagram of the structure as a whole. You could start with that because you have 3 unknowns, you could solve for that. But rule of thumb, the procedure that I'm suggesting, always to start with a free body diagram with the minimum number of unknowns because that's the easiest. So I'm going to start with free body diagram number 2, which is that pulley. Write summation of forces along x is equal to 0. That gives you dx minus 300 equal to 0. So dx is 300 pounds. Summation of forces along y is equal to 0. Gives you dy minus 300 is equal to 0. dy comes out to be 300 pounds. Okay, so that free body diagram is up. Now you go to the next free body diagram with least number of unknowns, and that is free body diagram number 1. You have 3 unknowns. Take summation of moments about this point. Summation of moments at A is equal to 0. So you have RF, distance 6, counterclockwise. This force 300, distance of 4 and 6, 10, counterclockwise. So RF comes out to be 500 pounds and positive. Okay. Summation of forces along x is equal to 0. There is no force except AX. So AX comes out to be 0. Summation of forces along y is equal to 0. Here you have AY plus 500 minus 300 equal to 0. That means AY comes out to be negative 200. So the assumed direction is wrong. So I'm going to correct that here, which means correct it here. And you're done with this. You found this. You found this. You found this. So this free body diagram is out. How many free body diagrams do you have left? 1, 2, 3. You have, let's see how many unknowns, right? And oh, by the way, I gotta put this. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. 1, 2, 3, 4. Again, I can choose any of them, but I will start with this guy because it helps me to find those unknowns easier. Okay, so I'll consider this guy. And what do? I take summation of moments at C is equal to 0. So I have only one unknown, which is EX, because EY goes through that same point too. EX is counterclockwise moment times this distance is 4, okay? As you can see, 300 is counterclockwise, so it's positive. And this distance is 3, because the radius of this pulley was 1, so this is 3. And this goes through that, and that's the only equation you have. So you have EX, that comes out to be, okay, I have that here, EX 225 pounds positive. Okay, so you're done with that. Now, summation of forces along x being 0 in this free body diagram, I give you Cx plus 300 minus 225 equal to 0. So Cx comes out to be 75 pounds and comes out to be what? Negative. That means the assumed direction for Cx is wrong. So I have to correct that here. I have to correct that here. All right. Now put the positive sign there. What else?
How did you get
Summation of,
negative for 225?
no, Ex was 225. It came out to be positive. So that means the assumed direction is correct.
Okay, so then for the sum of forces in the x equals 0, you'd have a positive 225, a positive 300, and then Cx, right?
No, I have a negative 225 because it is in the, see, this is in the negative direction of X. The direction is correct, but the algebraic summation is something else. Summation of forces along X is an algebraic summation. This force, its direction is correct, but since it is that acting in the negative direction of X, in this equation would be negative. See what I'm saying?
Well, if we solved it to find a positive value, how would we know it's in the negative direction of x?
So the positive value, what it means is that the assumed direction is correct. Okay? So if this came out to be positive from the summation of moments equation, you end up with a positive value for Ex. That means the direction you had assumed for this is correct. Okay? So the force is acting in this direction. Now you want to write summation of forces along X is equal to 0. You look at the forces that you have. You have this force, and this force. Cx, you had assumed is direction, is in that direction. So it was positive. 300 is in the positive direction of x, it is positive. 225 is in the negative direction of x, it is negative, equal to 0. What you're thinking is you're mixing the direction with the magnitude. The positive magnitude means the direction, the assumed direction here is correct. But when it comes to writing the forces along the direction of x, right? This force is acting this way. So in this algebraic equation, this would be a negative sign. Can you see that?
Yeah, I see that.
Sure. So, but that's a very important question. So unfortunately, I could not finish this problem. However, what I will do, I would strongly recommend you solve for all the unknowns, and I'm going to give you all the answers here, and make sure you solve this problem. So I'm going to write these down. EY comes out to be correct direction, 600 pounds. Okay. BY comes out to be here is going to come out to be wrong and would be downward, and you have to change that. And the value comes out to be 300 pounds. Okay. We solve for EX, EY, we didn't solve for EY comes out to be all, the correct direction. And EY will be also, oh, I wrote it down already, 600 pounds. What am I doing here? Okay. And that's it. Those are the unknowns that we had to solve for. And then you realize that once you solve for all these unknowns, you end up with one free body diagram that you have not used. Use that to verify your answers. Okay?
Thank you,
Any
Professor.
questions? Thank you. So let me stop here.